So, good afternoon. We are back with the second part of this class on quality of service over IP networks. And tonight we will be talking about scheduling. Let me share some slides with you. Let me see. I'm sorry, I have a problem with it. Okay, now let's see if this works. No, it still doesn't like to show me this one. I don't know why, but let's try it again now. I'm sorry, guys, but you know, technology doesn't always work at the first attempt. Okay, so here we go. And now you should basically see where we stopped last time. So let me actually go a little bit back. We saw last time these 4 principles for quality of service over IP or over communication networks, more in general. So packet classification or packet marking, the need for isolation, scheduling and policing. This is where we will focus on tonight. High resource utilization and call admission. Okay, so tonight we'll talk about scheduling. What do we mean by scheduling? Well, actually, scheduling is a well-known concept in queuing theory. And I actually warmly invite you, if something is not clear of what I will be talking about tonight, to look at Kleinrock's book, where you can actually find all these concepts explained with a number of simple examples, which I believe can help you understand things exactly. So we talk about one queuing system here with one server. We have a number of jobs which are queued, and we have spaces. What do we mean by spaces is basically kind of the maximum amount of jobs that can be queued in the system. And in our case, actually, the server is the link, the outgoing link from one router. The spaces is actually the buffer, the waiting area, actually, how it is called, is the buffer in the router. And the jobs are, of course, the packets. So the point is to decide, let's say that we just served one packet, which one shall we serve next? Now, of course, most of you would think that the natural answer is to schedule the one which has been there for the longest time, the one which arrived first. First in, first out, or first to come, first to serve. However, in many cases, this scheduling discipline is not actually the optimal choice. Another possible choice is, albeit is quite counterintuitive, is the last in, first out. So we basically serve next the last packet which arrived, or last to come, first to serve. It looks awkward, but there are actually cases in which this discipline is a better choice than FIFO. We can have priority. So, for example, well, I have classes, I have packets with different priority, and I serve the one with the highest priority. I don't care when it arrived, but I just basically serve it first. Or I can have packets belonging to different classes. I can associate classes with different level of priorities, or I can do other things. This is not actually the whole picture, because another important thing is to understand what to do when the buffer is full. Which packet should I drop? So I have a buffer which is full, there is no space, I cannot put another packet in the buffer, and I have one packet arriving. What do I do? Now, of course, the most obvious thing would be to do tail drop. So I basically drop the last packet that arrives. So the buffer is full, one packet arrives, and I drop that packet that just arrived, right? However, again, there are cases in which, well, this is not really the best thing to do. So I can actually come up with different discard policies, such as head drop. So I actually drop the one which has been waiting for the longest time in the buffer, the first one. I can have some priority discarding. So I have different level of priorities, and I discard, let's say, the packet with the lowest priority. I can base it on classes, or I can actually do something which looks really stupid, which is to drop packets at random. So I just select randomly one packet and I drop it. And this seems stupid, but actually you might be surprised to know that a variation of this policy is implemented in actually quite a number of commercial routers. It's called RED, Random Early Discard. And the reason is that this policy, dropping packets at random, is very good for TCP flows. We don't have time to go into it in details, but if you look for RED, R-E-D, you will find a number of papers that explain why this is the case. Okay, so here, okay, we just basically have what we just saw before, and we have this model that we will be working on. So we have the server, which is the links, we have the queue, which is the waiting area, the buffer, and we have arrivals of packets. Okay, so why do we need a non-trivial scheduling discipline? Well, the reason is that the per connection delay, bandwidth, and loss, so all the KPIs that we talked about, are determined by the scheduling discipline. Why so? Well, assuming we have a quality of service aware router, so something which cares about quality of service, which is not the case in standard IP routers, right? So what it can do is that basically by changing the service order, it can allocate different delays to different connections. If I give higher priority to packets from one connection, I serve them first, they will have a lower delay. That's quite trivial to understand. Another thing which is quite apparent is that it can easily allocate different bandwidths to different connections by, let's say, serving at least a given number of packets from a connection in a given time interval. So again, if I force the router to serve at least a given amount of packets from one of the connections, what I am actually doing is that I am guaranteeing a minimum bandwidth to that specific connection. And last but not least, of course, I can also impact the packet loss rate, by giving, for example, more or fewer buffers, or by playing with the discard policy. Again, I can apply priority, so I can, in a sense, force some higher packet error rate for some specific connections. So let's start with the simplest example, which is FIFO scheduling, first in, first out. The first packet that arrives is the first packet that gets served. What is the problem with it? Well, the main disadvantage with it is that the scheduler cannot differentiate among connections. So if I just care about the order at which packets arrive to my buffer, I cannot explicitly allocate to some connections some lower delays than other connections. I actually need to come up with a more sophisticated scheduling, which of course has a cost. But I have some fundamental limitations in the degrees of freedom that I have in the design of my scheduling policy. And in particular, I have the famous conservation law that states that the sum of the mean queuing delays received by the set of multiplexed connections weighted by their fair share of the links load is independent of the scheduling discipline. What does it mean? Well, it basically means that given a system which has a finite bandwidth, I have an overall limit in the amount of bandwidth that I can allocate to different flows. And second, there is a relationship between the the bandwidth that I allocate to connections and the delay that they experience. And if you check on Kleinrock's book, you will see some more explanations about this one. So what are the requirements for a good scheduling discipline? There are 4 key requirements. First, ease of implementation. Routers work at extremely high rate, which is basically the rate at which well, packets are sent out on the link. So if I have, let's say, 100 gigabit per second outgoing link, well, you can imagine what is the rate at which I need to pick packets. I basically need to do it every few microseconds. So I need a scheduler that is very fast in taking decision. But doesn't which computational complexity doesn't depend on the buffer size or on the amount of packets in the buffer, but it's actually a constant. Second, fairness and protection. I want one misbehaving connection not to disrupt all over connections. And of course, FIFO is not good for that, because basically if a connection sends a lot of packet, it can starvate the other connections. The other connections don't get anything. Ideally, I would like to have some performance bounds, which can be deterministic or statistical, and they can actually be in terms of bandwidth, in terms of delay. Typically, they are given in terms of delay, as we will see in a couple of classes, delay jitter, and packet losses. And last but not least, as one of the 4 pillars is admission control, I want a scheduling discipline but makes it easy to design admission control policies. Is it all? Well, another point I want to care about is actually fairness. We talked before about isolation, and fairness is just the other side of the coin. So what do we mean by it? It basically means that we want to make sure that all flows get some fair amount of bandwidth. But there isn't one single flow, even if it's not misbehaving, but maybe it's the top priority one, that gets most of the bandwidth, and the others don't get anything. The concept of fair share, it's actually that I can allocate a user with a small demand what it wants. So I basically make all the users with a small demand happy. And then I distribute in an equal way what is left, the unused resources, to the big users. What I'm doing, if I apply this policy, is that I'm actually maximizing the minimum share of a source whose demand is not fully satisfied. And this is basically why this policy is called max-min fair share. So what I do, I basically allocate resources in order of increasing demand. I first serve the ones with the smallest demand. No source gets a resource share larger than its demand, and sources with unsatisfied demands get an equal share of the resource. This is one option. So, in designing a scheduling disciplines, what are the degrees of freedom that I have? I basically have 4 degrees of freedom. 1, the number of priority levels. I want to have priority levels. How many priority levels do I put into my system? Typically 3. I need to decide whether each level is work-conserving or non-work-conserving. What it means? Well, a scheduler is said to be work-conserving in case if it respects the following condition. If there is at least one packet in the buffer, the server is actually serving it. What it means is that as long as there is work to do, it doesn't get idle. It looks trivial to say, oh, but work on service is always better than non-work on serving. But, well, life is actually quite complex, so this is not really the case. Second, the degree of aggregation of connections within a level, within a priority level. Do I associate it to a single source destination pair? Do I associate it to all, let's say, video connections? How do I do it? This is, of course, one of the things I need to specify. And last but not least, the service order within a level. So within a given level, how do I serve packets? Is it the first in, first out, or is it a different one? And of course, each feature comes at some cost, and there is always a trade-off, as in all engineering design problems. So if I have a small local area network, well, probably a single priority first in, first out scheduler is good enough. Or maybe I want to have a two priority scheduler. In one, I put all the batch processing traffic, like FTP or whatever. In the other one, I put all the interactive traffic, so Skype, but also web browsing and so on and so forth. However, if I'm going to a heavily loaded wide area public switch with possibly non-cooperative users, so users who try to cheat the system and misbehave, I definitely need a more sophisticated scheduling discipline. Okay, so one potential scheme, one traditional scheme, is priority scheduling. What it does, it just transmits the highest priority queued packets. So I have multiple classes. Each class is assigned a different level of priorities. And of course, classes might depend on marking or overheader information, IP source destination, port number, and so on and so forth. But this situation is the one that you see below in the figure. So here I have two classes, one which is the red one, which is high priority traffic, and one which is the green one, which is low priority traffic. Once I get to my router, I classify them, I split them into two separate buffers, and I'm going to serve the red buffer first. If there is nothing in the red buffer, then I serve the green buffer. And you have on the right-hand side a simple example where you see arrivals of packets, which one gets served, and the departure. And you basically see, for example, that packet 3, which is red, so it's actually high priority, arrives after packet 2, which is green, so low priority, but it actually gets served before. Okay, so of course here I need to understand how many levels of priority. Typically for priority scheduling 3, it's good enough. However, I might have problems with starvation, because here, as long as there are red packets, I'm not going to serve the green packets. So I can actually have green packets that keep waiting forever, or, well, more realistically, for a very long time. So what I need there, I actually need to make sure that my admission control works well, and I might want to have some traffic policing to restrict the service rates from all but the lowest priority level. So that in a sense, I can make sure that the green traffic, the poor guy with a low priority level, still gets a little bit of bandwidth. And the big advantage of priority scheduling is that this is very, very simple to implement. Another option is round-robin scheduling, which is a variation of the previous one. So I basically put packets from different classes into different buffers, into different queues. But here, what I do is that I cyclically scan class queues, serving one from each class, if available. So what I do, basically, I first serve one packet from the red, then one packet from the green, then one packet from the red, then one packet from the green, and so on and so forth. What is the big advantage here is that it provides protection against misbehaving sources. Because in this case, well, it doesn't really matter how many packets the red source is injecting into the system. Still, the green gets its turn, for sure. This is guaranteed by design, which means that we are also guaranteeing a minimum bandwidth to every connection. Because in each cycle, we are going to serve at least once each single queue. Of course, this is the problem, but it doesn't really differentiate. So what I can do, I put the two things together, and I come up with what is known as weighted fair queuing, or generalized round robin. So what I do, in this case, here I have an example with 3 classes, red, green, and blue. I basically classify arrivals, I put them into separate queues, and then each class is getting a weighted amount of service in each cycle. So for example, in each cycle, I serve 3 packets from the red, let's say 2 from the green, and 1 from the blue. And I keep on cycling. So in this case, the cycle would actually be 6 packets, 3 from red, 2 from green, 1 from blue. So this concludes this part, this class actually. And in the next one, we will discuss about traffic policing. If you have never seen anything about scheduling, this might have been a bit fast. So please go back and check Klein Rock's book to have some more detail. Talk to you soon.